Okay, so let's solve exact same problem. We need to calculate the same average acceleration, so which is v2 minus v1 divided by delta t. So let's renotate our velocity change as delta v divided by delta delta t. So delta t here is time of travel, so that's t2 minus t1, so which is 6 minus h2, and this is equal to 4 seconds. So this is our velocity v2, so this is our velocity v1, and again, like, we just need to calculate our delta v. In the previous case, we applied tip to tail rule, added vectors geometrically, applied sine and cosine law, and calculated that delta v, magnitude and its direction. Now we are going to apply a component approach. We are going to split our vectors along horizontal and vertical directions, and we are going to calculate components of delta v. And then using those components, we are going to recreate that vector, adding them up. Okay, so let's maybe show those components. We usually don't do it, but here let's do it. It's just, I would say, not complete waste of time, but some waste of time, I would say, because usually those are quite straightforward, and right away we write those component equations without showing like those components, because sometimes it actually overloads the picture, and if you have a whole bunch of vectors, obviously this is going to be quite messy. But here that's fine. So we have quite a good schematic, so we can do it. So this one is going to be our v2x vector. So this is going to be v2y vector, right? And we'll do the same here. So this is going to be our y component. And this is going to be our x component. Here. Okay. So this is going to be our v1x here. And this is going to be v1y vector. Okay, and this angle is 50 degrees. So I like to use same reference like for everything for this type of problems. Also, to define signs in our component equations, we are going to introduce like some convention. So this is quite usual approach, so which is used in high school, and I would say that's enough to solve all those simple problems on the high school level, junior high, high school. So instead of introducing the unit vectors, right, and coordinates of the vectors, like, and that consistent reference, usually like in mechanics, like that's counterclockwise relative to horizontal axis. So we will introduce very simple convention, so which will define signs in our component equations. So if our vectors are pointing to the right, they will go with plus. If our vectors are pointing up, they will go with plus. If they point to the left, they will go with minus, and if they point down, they will go with minus as well. Okay, so this is good. So let's write those components. Okay, so for delta v, this is vector, delta v x, so that's v2x. Let's maybe write it down, so v2x minus, since it's the difference, minus v1x. Okay, so v2x is pointing to the right, so it goes with plus, and its magnitude is 55 multiplied by cosine of 15 degrees. Okay, so then minus that component is positive, so since it's pointing to the right, and that minus goes like from this difference. And this is going to be 40 multiplied by cosine of 50 degrees. Okay, so that's written right there. So it's 55 multiplied by cosine 15 minus 40 multiplied by cosine 15. This is 27.4. So this is equal to 27 meters per second. Okay, so this is good. So let's calculate delta v y. And this is v2y minus v1y. And this is equal to, so v2y, so it's pointing up, and there is 55 multiplied by a sine of 15 degrees minus, so this is that minus right there, right? And minus, and then v1y pointing down, it goes with minus. Okay, that's another minus here, and this is 40 multiplied by, so 40 multiplied by sine of 50 degrees. Okay, and this is equal to, so we have 55 multiplied by 15, so that's sine, and then minus on minus gives us plus 40 multiplied by 50 and sine. This is equal to 44.87. So it's 44.9, right? So 44.9 meters per second. You can go a bit more accurate here, so maybe like up to the fourth, like, or even fifth significant figure, so whatever you like. Okay, so this is good. So we have two components, both of them are positive, right? So both of them are positive, so that means this is pointing to the right, and this is pointing up. Okay, so this is good. This is good. Now we need to recreate our resultant vector, delta v. So let's do it. So we have 27. So let's maybe do it up to scale more or less. So we have on this 27, something like this, right? And this is about less than twice, but so it's significantly longer. So let's like this here longer, right? Okay, so let's something like that. Okay, good. So this is good. So let's draw the resultant directions here. Like this, right? So let's show our resultant and then also draw directions of those vectors as well. Something like this. Okay, good. So this is our delta V. This is delta V. Okay. So this is 44.9, right? So 44.9 meters per second. And this angle is some angle theta, which defines direction of our delta V. And this one is 27 meters per second. Okay, so we can calculate delta V as squared root of 44.9 squared plus 27.4 squared. Okay, so let's see how much is that. So it's 44.9 squared, right? Plus 27.4 squared. Okay, and we take the square root of this, so 52.6. 52.6 meters per second. Okay, so tangent of this angle is equal to 44.9 divided by 27.4. So let's right away calculate that angle. Okay, so we have 44.9, right, divided by 27.4. Okay, and let's take our tangent of this 58.6. As you can see, we've got the same result, exact same result, 58.6. 58.6. Okay, so our delta V is equal to 52.6 meters per second at 58.6 degrees relative to the horizontal line. Okay, so let's finish this calculation. It's again exact same as in the previous problem. So we've got 52.6, right? So 52.6 divided by 4. (13.2) up to the third significant figure meters per second squared, and we've got exact same angle. Okay, so we can write the answer again. Our acceleration is equal to 13.2 meters per second squared at 58.6 degrees relative to the horizontal line. As you can see, it's about the same in terms of labor. And so some people like to use component method. So some people like to use geometrical method. I would say it's about the same amount of work. Okay, so that's it for this video, and then the next video, in the next video we will solve some projectile motion problem.